we discussed about higher order schemes and implicit scheme. So we covered Euler, forward, backward, predictor corrector, and Rangakutta. Okay, and okay, so you are all set. In fact, you can solve quite a bit of problems, but I will tell you a few more important points about ODE solvers today. Okay, so next is multi-step methods. So what is multi-step method? So if you look at, go back, Euler's scheme, if you recall, we had gone to xn plus 1, given xn, and computing f at xn. Okay. In Euler backward scheme, it was xn plus 1, forward, ahead, you know. We are not using something in the past. So this is Tn. You go to Tn plus 1, like that. But you are not using any value of the past, like Tn minus 1. I'm not using this, or Tn minus 2. So this is single step method. You use Tn to get to Tn plus 1. Okay. Now multi-step means I not only use Tn, but I use Tn minus 1, Tn minus 2, and so on. Okay. This is called multi-step method. So we did one multi-step method, if you recall. Leapfrog was done, was mentioned in the earlier classes. So here we go from Tn minus 1 to Tn plus 1. That means I'm also using Tn. Okay, so in fact, the value of the function is computed at Tn here, and I use initial condition, or rather state of n minus 1, Tn minus 1. Okay, so we use x here, and value of f is computed here, okay, and to reach here. Okay. So xn minus 1 plus 2 delta t. So the step is 2 delta t. 2 delta t, and value of the function in the midpoint. In fact, it's a midpoint method, f at midpoint, and if you do this, then you get to xn plus 1. Okay, so this is called leapfrog, and this frog, you know, leaps forward. So it's using the midpoint as state of the midpoint for computing f. Okay, now this method has certain advantages. Okay, imagine that I want to go from backward. Okay, so I go from Tn plus 1 to Tn minus 1. I go back. So what will that be? My delta t is negative, right? When I'm going backward in time. So instead of 2 delta t, you replace by minus 2 delta t. And I'm computing value of the function at the midpoint. Midpoint is the same, which is xn and Tn. So if when I go back, I go from xn plus 1 to xn minus 1 by computing f at the midpoint. Okay, I hope this is clear. Now, these two equations are exactly the same. Right? You can see if I just take this part to the left side, I get the top equation. Okay, so so leapfrog method is symmetric under time reversal. So this operation, t going to minus t, or you go, instead of going forward, you go backward. That's called basically time reverse motion. And for leapfrog method, if you go forward or backward, your equation remains the same. But this is not the case for other methods which we discussed so far. So let's look at Euler forward. Euler forward is xn plus 1 equal to xn. I go ahead, huh? So delta t f xn tn. What if I go back in time? So back in time will be going from tn plus 1 to tn. Apply Euler only, okay? So this will be, my final state is xn. I go like that, right? So go like that. Equal to xn plus 1 is great. Minus delta t. I go back in time, so delta t is negative. F, where do you compute f? F at the current location, here. It will be x n plus 1 t n plus 1. Okay. Now you can clearly see that this equation is not same as this equation, right? When I take this to the left hand side, I do not get Euler forward in the forward direction. Okay. So Euler forward is not symmetric under T2 minus T transformation. Okay. And you can show that same thing for RK2 or Euler backward as well. Now, why do we worry about time reversal? Okay. Now, there are symmetries in physics, no? Okay. Most of you are from physics department, so there are symmetries in physical systems. So, symmetry under time translation, space rotation, and under mirror symmetry as well as time reversal symmetry. Okay. Time reversal symmetry is not exact. That means it's not respected by all systems. Okay, especially for weak interaction of nuclear physics, a time reversal symmetry is not respected. But in most interactions, like gravity and electrodynamics, time reversal symmetry is respected. So if you look at Newton's laws, mx double dot equal to force. Now imagine force is gravity force. So mg. Okay, now these are vectors. Now, under T2 minus T, what happens to the equation? So what happens to x double dot? It remains. So T2 minus T, so I do this. So I get, first derivative will get a minus sign. But if I do another derivative, minus x whole square, minus T also, minus T square. So minus becomes basically a plus, 2 minus, okay. So the acceleration is the same under T2 minus T. And G, of course, has no, it is the same. When you go forward or backward, gravity is same. Okay, when Earth is there and it is. So, so this equation is symmetric under time reversal. Symmetric under T2 minus T operation. It has a consequence. Now, I will not detail this, but you should, I mean, this is important to know. So, if I have a projectile in vacuum, okay, in vacuum, it follows a parabolic path and reaches here. So, I go from A to B. Now, imagine that I reverse this motion, okay. So, reverse this motion means just imagine that I play this movie backward, or I record this projectile motion in a video camera and play the video camera backward. So the projectile will go back in time. Okay, so it will just, so this was, let's say, happened at 11 o'clock and this will started at 10:55. So I just run it backward. Okay, so in the movie it will come back. Of course, movie is played backward, movie will come back. But what if I do an experiment where I start from B with exactly same velocity as the reversed motion, the same velocity as the reverse motion? Where will it come? Will it come back to A or not? If there is no friction, no air friction, then it will come back to A. Okay, because Newton's law is symmetric under time reversal. Okay, I mean, of course, this is straightforward that projectile motion is symmetric from like that or like this. Of course, when you put friction, then the equation is also not symmetric, as well as the projectile motion is not symmetric, right? So if I put gamma x dot is one such force, then this equation is not symmetric because x dot will change sign, right? T going to minus t. Okay, so and of course I know that forward motion is not really a parabola, it's like this. And backward motion, if I just go backward from here, it will be even smaller, like that. Okay, so forward motion and backward motion are not same in the presence of friction. Okay, so of course friction breaks the time of the symmetry. Okay, but fundamental forces like gravity and electrodynamics do not. Okay. Now, if you want to read more about this, there are tons of material, books written on it. But I have a paper on this. If you can look at in the website. So this is EPJB. Okay, European Journal of Physics B. I have some interesting way to look at it, but of course, it's beyond this today's topic. I can't cover in this course. It's 2018, 2019 or 2001. I don't remember. Okay, you can just say you'll see time arrow of time. Okay, the title has arrow of time in my website. Okay, there are some point of view which I am trying to propose, but anyway. So if somebody is interested, can have a look. Okay, now why do I worry about this? So if I look at I might run out of space in that slide. If I'm trying to solve equation of motion or Newton's laws with computer, then I have to make sure that my computer solutions are symmetric under time reversal. So like projectile motion, if I'm trying to simulate, then if I go back in time for the projectile, I should get back to the original position. Okay, so my ODE solvers should have that feature. If not, then my ODE solver will not, it's not accurate. Okay, so leapfrog method is accurate. Okay, for time reversal symmetry. Of course, there are errors, numerical errors, which I'm going to come soon. But there will be, I mean, some energy conservation will hold on the average. Okay, it will oscillate, but in Euler equation, energy conservation does not hold. It either increases or decreases. Okay, the error, but in leapfrog, it will oscillate. Sometimes more, sometimes less, like that. Okay, so these are useful. Of course, numerical errors are there, but we want to use a scheme so that they kind of cancel in such a way that my conservation laws are approximately valid. Okay, that's the idea. Okay, and let's look at stability of leapfrog method. So x dot is alpha x, right? So this is my equation. So I know that the problem when alpha is negative. Okay, so now let's see what happens for this case. So I just substitute. This is straightforward. This one. So I just substitute in the right hand side. So I get this stuff. Now this equation is a pretty tricky one, right? Here I have xn minus 1, xn. So I can't. It looks slightly problematic to solve, right? We have one equation and I have xn plus 1 depends on xn minus 1 as well as xn. So it's not straightforward to solve. But let's try a solution which is growing in time, xn, rho to the power n. Okay, it turns out it's a valid solution. It works. How do I see that? So this will be rho n plus 1. This will be rho n minus 1 plus 2 alpha delta t rho n. So rho n will cancel and you get, so this is rho and this 1 by rho. So I just multiply by rho both sides and cancel rho to the power n. Okay? So rho squared equal to 1 plus 2 alpha delta t. So this is the rho. Okay. Or basically divide by rho n minus 1 if you like all sides. So this is a quadratic equation in rho. So it has two solutions, right? Now the two solutions I put it now is there. And these two solutions, you can, it's kind of hidden, but let me just write this. So rho 1, 2 is alpha delta t plus minus square root alpha delta t squared plus 1. Okay. Now, so my general solution will be xn is c1 rho to the power n plus c2 rho 2 to the power n. Okay. So both of them satisfy. So it is a linear equation, so superposition will hold, and that is my solution. Now, this solution has a problem. What is the problem? If you expand this rho 1, 2, Taylor expansion. So alpha delta t is supposed to be small, right, compared to 1. So alpha delta t is small compared to 1. So when I expand it, I get these two expressions, rho 1 and rho 2. Now it turns out rho 2 is minus 1 plus alpha delta t, like that. This is just simple Taylor expansion, assuming alpha delta t to be small. Okay. Now, okay, so which one is this? Is a correct expression? Now alpha delta t is small, no? So I expect rho n plus 1, xn plus 1 to be close to xn. Okay. So the first one is a correct solution, not the second one. Second one is switching sign, is minus 1, right? Second one is definitely a spurious solution. Okay. Any answer from mathematics is not a valid answer. Okay, so we know it. So here, of course, the solution is decreasing, but it is not switching sign. Okay, so I need to choose the first solution. Okay, but of course, when I solve in a computer, I have to be extra cautious. Otherwise, typically, we give the initial condition, it will just advance in time, and it is going to take both rho 1 and rho 2. Okay, so we have to make sure. I mean, you have to keep doing it often, so that rho 2 is suppressed. Okay. Now, one more point for leapfrog, there is a initial condition itself is the issue. Right? What happens at initial condition? I have to, suppose I start with x0. I want to go to x1, right? So then I need delta t, 2 alpha delta t. Basically, I need x of minus 1, one step before, right? So I go from 0 to delta t, but I also need the value at minus delta t. So like that. So when you go from, so the leapfrog has, or any multi-step method has this issue, that we need to, when you set the initial condition, when you go from the initial condition itself, 0 delta t, I need minus delta t, okay, which is not available. So starting for leapfrog, you can start with Euler, first step, okay, or RK2, no issue. But first step has to be single step method. But then after first step is done, then we have this and this, right? We have this and this after first step. Then I can go to 2 delta t. And now I can use this and that to reach here. Okay. So starting is the issue with multi-step. Okay. Now, so you have to be careful. I don't want to discuss much more than this. You can look at the notes. There are also this book by Fazizar, which has more detail. So idea is to keep cancelling row 2 by choosing appropriate initial condition. Okay. So you can just, in fact, you can choose this. I describe in the notes. So we choose appropriate initial condition so that row 2 is 0. And also in between, once we run, let's say 100 time steps, then you refresh by avoiding leapfrog for a few steps and just use RK2, for example. Then again start leapfrog. So leapfrog has some of these issues. Now there are other multi-step methods. I'll just mention one more, Adams-Bashforth. Okay. So what is Adams-Bashforth? I go from xn to xn plus 1, but I use quite a few xn's. Okay. So xn minus 1, n minus m going from 0 to k minus 1. So m is 0 will be xn, of course, which is current state. M equal to 1 will be xn minus 1. M equal to 2 will be xn minus 2. You can choose how many steps you like. So this is a table. It is from book by Chapra. The first one is straightforward. M equal to 0. I just have this beta. So this beta is the coefficient which are listed here. Okay. So this is Euler forward. But this is Adams-Bashforth two-step method. Okay. So I just listed here. So if you look at this one, it is going to be the first one, this beta 2 0 will be 3 by 2. Okay, this 3 by 2. And next one is minus half, minus 1 by 2. Okay, so this one is quite popular, Adams-Bashforth two-step method. Okay, so a lot of people use this. Okay, so I think that's about it for multi-step method.